on right now. I got the recorder turned on. All right, so I did find a solution to the problem. If you are using the the desktop computer in the lab, you can use Java. It's quite a few steps, okay? So I'm not really sure whether I want to show it now or later in the class, like when we're close to the lab time, because not everybody needs to follow these instructions, but for those who want to continue to use the desktop computers in the lab, these are the instructions. Um, we might have a better solution, soon, but right now this is the only solution I have found at this point. And this is the only class that is impacted by Java getting uninstalled from these labs. Because the other class, downstairs, they're using the virtual machines to begin with, and the Java has not been uninstalled from the Windows virtual machines, but I think it's going to be like that also, soon. So they're going to have to suffer the same fate that we do. All right. So with all that said, I am going to start today's lecture now. And based on what we talked about already, so what I want to do is to kind of show you the processor again. So let me go to my folder and get the processor shown here. Give me a second here. Okay, they are all in the same folder. Okay, let me show you what I'm doing because I'm doing everything on the command line. So we have jar dash jar and then logisim and then processors. All right, so there we go. All right. So this is what we have, as the processor that we'll be using for the rest of this entire semester. Um, I know it looks like a lot of stuff, to process all at the same time, but I'm gonna give you a kind of like a guide of how to look at this whole thing. We're gonna walk through this whole thing a few times also. So when we get to that point, it is important to kind of note the time of when I start to talk about when at what time. When I start to talk, when I start to talk about what, you know, and that's going to be important because this allows you to go back to the video recording and just to replay certain portions if you want to. And I know some of you guys can also even make a remix of the class videos. Just all the major moments, all the important stuff, just kind of do all the editing that you want to do, which is, okay. You can go ahead and do that if that is what you wish to do. All right. So what do you guys think of the lab that was due this morning? Yep.
I had a quick question because
Mm-hmm.
just specific to mine, you left a note that said um, pin C needs to transition from 0 to 1.
Mm-hmm.
Quote unquote, rising edge to mirrored B port. And I'm not quite sure what that meant because I'm pretty sure.
Okay. So according to the description, you need to make changes in a certain way. So the sequencing of the changes is important. Um, all right, so let's go back to that particular assignment, and I'm going to show you what I mean by that. So I'm going to reconstruct the entire circuit, probably without labeling the input pins. And that is using a register, which is under the memory category. And the output pin is not important other than just confirming that you got the right content in the register, which you can also see from the hexadecimal digits inside the register. So obviously it's not going to like it because both of these pins need to be 8-bit wide. So I can select both and change both to 8-bit wide at the same time. There we go. This is the enable. Okay, there we go. And this is going to hook up to the clock. And this is for reset. So, oops. Let me do that one more time. There we go. This one goes to the reset. And I think this is labeled A. And then we have this one labeled B. And this one labeled C. and this one labeled D. All right, and this is labeled E. And I'm not sure, did we work with only 3 bits? I think we were supposed to work with only 3 bits.
I guess it doesn't matter.
That's okay. I can change all at the same time to 3 bits. This is the convenient part of being able to select a bunch of stuff and change all of them, to the same bit width at the same time. Okay. So the question is asking, how do we get the register to output 011 as a bit pattern? Yep.
So just kind of go through what I went. I like set the input bit A to, what's supposed to be 011.
Uh-huh.
And now, well, you have to enable it now with B, so you have to turn B on.
Mm-hmm.
And then I turn C.
From a 0 to a 1.
I turned C on.
Okay, so the question is it clear in the instruction that this is the sequence? Because if the order is not the same, it's not going to work.
I felt like I labeled it exactly like that. Like I said, step 1 set pin to 00. What I stepped through is how I just explained it now. I set A to 011.
Okay, I have to look at the actual description again to see if I missed something. That's entirely possible.
Okay.
But the most important point is we need to make sure that you set up everything else. Now, how the ordering of setting up A, B, and D is not important. Okay, they just need to be set up first. But then C turning from 0 to a 1 has to be the last step. That part has to be explicit. I have to see that it has a significance. That turning on C, you're going from 0 to 1, is the last step that you need to do.
Never mind, I made a mistake. I did see, I turned it on, but on my steps, I put 0. So,
oh, okay. Okay, yeah. The lab does not carry a lot of points, especially if we're only looking at one single lab. It's like, the point value is, I wouldn't say totally insignificant because they all add up, but I would not be too worried about it. But the most important point here is the transition is what makes it work. So if I want to change the bit pattern to 001 instead, I can enable and disable all day long. Nothing happens, right? It is only when I have a rising edge transition at the clock, which is this little triangular thing. It's only when it sees a transition from 0 to a 1, then it mirrors. Then it mirrors whatever it sees as the D port of the register to the Q port, which is the output. So that part is very, very important because the processor depends on this feature of the register to get its own things done. Okay? In fact, I am going to look at this thing here, and since I already have it, I'm going to make some additions to this circuit just so that we have an interesting thing that we can look at. Okay? So what I'll do is I'm changing this to add an adder to it, to the whole thing. And the adder has 2 inputs. These are the 2 numbers that we are adding. This is the output of the sum. The actual sum is the output. And this is the carry in, and this is the output. So what I'll do is I'm going to make it add 1, okay? So I would go to the wiring and pick up a constant. You guys already know how to pick up a constant because that's also needed for your lab due this morning. So we pick up a constant, and we can say a constant of 1 to, I got 2 ways to do this. I'm going to do it the same way as in the processor, which is putting a 1 into carry in. And then one of the input is just coming from the register's output. And I have to fix the adder to deal with only 3 bits and not 8, but that's easy. And then this one here, I can just give it a 0. So I will make another constant of a 8 or 3-bit 0, and make this the second input to the adder. In other words, I'm basically adding whatever the register has with 0. But since carry in, which is K0 from our perspective, is a 1, so I'm still effectively adding 1 to whatever the input is. And then I'll take out the input pin, okay, and just kind of route this thing around back to the input, like so. Okay, So right now the circuit is done, and you're not seeing the register going crazy, like just changing all that all continuously. It's because the clock pin is steady. The clock pin is just at a zero. We are not having any rising edges. So even though if you poke the wires, if you were to poke the input to the register, it is already a new value. This is already reflecting the new value, which is supposed to be 2. Why is it 2? Because the output of the register is 1. 1 plus 1 is 2. I mean, do okay so far. The adder is doing its job, but the register is not changing to a 2 because we are not giving it a rising edge yet. Is that okay? So now what happens if we give it a rising edge? It changes to 2. But it doesn't change to 3 automatically. It's not automatic because it's waiting for another rising edge to change to 3, and then 4, and then 5. And when it gets to 7, it would basically go back to 0 because everything is modulo 8 in this case. Are we doing okay so far with this circuit? This is a counter, and it counts up only when every time when you have a transition of the clock pin going from 0 to 1. So are there any questions about this particular circuit? Okay, all right, very good. And this is a good segue to get into some aspects of the processor. And I can show you what the lab looks like for today, okay? Because this way you know what kind of component you need to learn about in today's lab. So we are looking at more processor components. I have not released yet, okay? So the lab for today has not been released, but I will show you what components are going to be in the lab today. All right. So what we have today in the lab is something that looks like a multiplexer, except it's not. This is a demultiplexer. It does the opposite of a multiplexer. So from the lab on Monday, you know what a multiplexer does, right? It has multiple inputs, one person in the middle to kind of like, okay, I'm going to choose one of these inputs to become the output. That's what a multiplexer does. A demultiplexer is going the opposite way. So in this case, we have one single input, and then the demultiplexer is just choosing, okay, which one of the output should connect to the input. And that's all it does. So if you already understand what a multiplexer is, you just reverse the direction, and you have a demultiplexer. Is that okay? So that's the second question. And then the last question, which is, or the second, this is the, this is the first. This is the second one, which is a ROM. A ROM is nothing more than a table. You're looking up something. And then the last one is a RAM module. Did we talk about the RAM module in this class?
I don't think not. I think we
Nope.
briefly discussed it, but not really.
Okay, but I haven't really gone through the exercises, right? Okay, so this is something I can do in today's lecture, is to kind of go through how we use RAM in this class. Okay. So I think that is all that you need to do for today's lab. That's it. But you do need Logisim, which also means if you're not bringing your own device, you're going to have to follow the instructions in the latest announcement. It might take you about maybe 15 minutes, to set it up. Um, but other than that, we can still do it. Okay, it's just that we have to use the virtual machine to do it. All right. So I'm going to go back to LogicSim because now I'm going to show you what a RAM component looks like and how to make it work. The RAM component is probably the most complicated component in the entire processor as a single component. So we'll go to new, get a new circuit, and then we go to memory, pick up a RAM module. A RAM module is a specialization of a RAM module. It's just like RAM, but easier. So we are more focused on just a RAM module at this point. So this is a RAM module, and you can first look at all the ports that it has. It has an address port, has a select port, a clock port, a load port, a clear port, and a data port. So I'm just going to go around to describe what each port does. But the first thing we want to know about RAM is it is called random access memory, which implies, even though it doesn't say that, but it implies that you can get to any location, and it also kind of implies that you can overwrite the content at each location. Are we doing okay so far with those concepts? Okay. So when we pick up a RAM component, you can see that it has several attributes. The first one is how many bits are with the A port, and then the second one is how many bits do we have with the D port over here, and then the third one is one synchronous load, which is basically this is the load pin, and it is synchronous, which means we have a clock pin associated with when we want to update the content of RAM. So the first thing we need to know is inside a single RAM component, there are multiple locations. Okay, so this is not a register. A register has its own content, and that's it. Okay, every time you want to change a register, it is the value of the register. It's one thing. But the RAM component, on the other hand, has multiple locations in it. One way to look at this, if you want to relate this to concepts that you have already learned in CISP360, is that a register is kind of like int x, okay? X as a variable, as an integer, is one thing, right? Every time you update x, it's the value of x itself getting updated. RAM and ROM are more like arrays. So let me just kind of use a text editor to illustrate what I mean, because I want to give you the C code in order to explain the concept that I'm trying to explain here. All right, so here is my text editor. So int x, x is more like a register. A register is like x. Okay, a register is like x. On the other hand, if you have an array, depending on whether the array is const or not, it is more like a RAM or ROM. So if you have a const like this, okay, const int, let's say A1, okay, array 1, and we want to give it 4 elements, okay, and now you can specify the actual value in the array. So let's say 32 is one value, 145 is another value, -5 is one, and we'll pick, I don't know, one. Okay, fine. All right. So in this case, A1 is like a ROM component. Okay, it doesn't have one single value. It has 4 locations. There are 4 elements in it, and then you can designate and say, I want the first one, I want the second one, I want the third one, or I want the fourth one. Okay. So what about RAM? Okay, let me just comment here. A ROM is like A1. So RAM is just like that, okay, for the most part, except you don't have the const in front of it. So a RAM, random access memory component, is like A2. So can someone tell me, just from the looks of it, what is the main difference between A1 and A2? Yes?
You can change what's inside a RAM, like at each location, but you can't change it, like once the ROM has its values, then you can't change it.
That is correct. So ROM stands for read-only memory. So the name itself spells out exactly what you cannot do, which is to overwrite. Okay. RAM, on the other hand, as random access memory, doesn't quite say that it's overwritable, but it's sort of implied. All right. So I hope this is useful, because I'm trying to connect the concept that we are trying to learn right now in this class to concepts that you probably have learned already in your CISP 360. Unless your professor did not use the const word or did not talk about what const is about, then this may not relate as well. Are we good so far? Okay. All right. So when you use it, okay, so when you say x equals to a2 bracket, well, we'll say 1 over here, okay? So in this case, the expression of a2 bracket 1 is quote unquote the D port. It is the output. It is reflecting the content of the second element of A2. So in the same expression here, 1 is presented to the A port of RAM. So which one are we talking about? The one inside the square bracket. So whatever expression is inside the square bracket that allows you to specify which element do I want to access in the array, that is what you need to present to the A port of RAM and also ROM so that you can tell the component which location do I want to access. Is that okay? All right. So in some way, okay, in some way, the D port is the value of a designated or indexed, okay, of an indexed, oh, just right here, of an indexed element in RAM or ROM, and then the A port is the index of the element to be accessed. Is that okay? All right. All right, so with that said, let's go back and take a look at the RAM component in Logisim. So we now know what A is for. Okay, A is a port that will allow us to specify which location do we want to access or which element do we want to access. D is basically the actual content at that location. What about all of the other things? Well, let's talk about the simple ones first, which is cell. So select is basically like enable. If you remember enable of a D flip-flop, it's just called select here or chip select. So it's called select because it's actually the abbreviation of chip select. If you read the data sheet of RAM components, it is usually called CS for chip select and not just select. But it serves the same purpose as EN, which is enable. So what that means is if this particular port is a 0, the RAM component is going like, okay, I'm just not going to pay attention to anything. Okay, it is not doing a single thing. It is as if the component is not even there. Is that okay? That's what the chip select is for. If the chip select is a 1 in this case, it means the component has to pay attention to all of the other ports to understand what it's supposed to do. Is that okay? All right. So the next one is the clock. Okay, this little symbol here, it is not spelled out as CLK clock, but it really is the same thing as a clock of a register or the clock of an edge-sensitive D flip-flop. Okay, I hope you guys still remember what an edge-sensitive D flip-flop is. Okay, and we also talked about the clock of a register just today in class earlier. Okay, so this serves the same purpose. Okay, it controls the timing of when a location in the RAM component is going to be updated. Next one up is clear. This is the same thing as reset of the D flip-flop. So when clear is a 1, it will zero out the entire content of this particular RAM component. So it's a good thing to do when you're powering up a computer to assert the clear for a little bit of time. So that way, you start with known zeros in RAM as opposed to unknown content in RAM. So the one thing that we do not see in the register, because all of these are in registers already. So the only one thing that was not in the register is LD. So when you hover over, it tells you what it is. If it is a 1, that means we're trying to read the content of a location in RAM. But if it is a 0, it means we are trying to overwrite the content of a location in RAM. In other words, it's direction control. Are we reading? Are we accessing something by reading it? Or are we trying to change something in RAM? Are we doing okay so far? Okay. So if I want to use a conditional statement to kind of describe the behavior of RAM, it might look something like this. And this is also this is the first time that I use this method to explain what a RAM component does. So, so let's just say that RAM is a class, and lowercase RAM is the name of the object of that class. So The first thing is if RAM dot cell is does not equal to a 0, then we do the following. Otherwise, I skipped in over the entire conditional statement. So what that means is if RAM cell is not a 1, if it is a 0, I'm just going to do absolutely nothing. It's completely ignoring everything else. It's not trying to drive the D port. It's not trying to specify the content at the D port. It's not interpreting the A port. It's not interpreting the clock. Nothing. It absolutely does not do a single thing. So the next thing we need to know is whether the LD pin is a 1 or not. So this is the LD pin. So if the LD pin is a 1, then we go into one branch of the conditional statement. Otherwise, we go to a different branch of the same conditional statement. So this is typically how I would do my coding is, right inside the then branch, I would explain what it means to be here. So that means your LD is 1. This is a read cycle. And otherwise, LD is a 0. That means it's a write cycle. Is that okay so far? So I'm converting the documentation of RAM, how a RAM component works, into something that we are more familiar with, which is something that looks like C code. Well, C++, because this is different. Well, I mean, it can be C because your RAM can be a structure only. All right. So if it is a RAM read cycle, then it's pretty easy. The D port, so RAM.D. Oops, I should be using lowercase because we should be referring to the object and not the class. So ram.d, which is the data port, will now get the value of wherever we are trying to access, which is ram.content bracket, whatever is in ram.a. There we go. Okay, so this may be the part that takes a little bit of explaining, but it is also the most crucial part. Content is referring to all the bytes stored or all the locations stored in the single RAM component. That's what content is. But it's not one single value. It is a bunch of values, right? It's an array. So RAM.A is the port that we use to specify exactly which location of content do we want to access. And whatever that content is becomes the D port. So the D port is serving as an output in this case because it's trying to let the rest of the world know, hey, I got the content of that location that you want me to access is this, okay? So this is how a read cycle operates. The write cycle is a little bit more awkward, okay? The write cycle is waiting for a transition from a 0 to a 1 with a clock pin. So now the question is, how do we detect a rising edge of the clock pin as code, right? As pseudocode? Yes, go ahead.
You need like an and statement, like a condition.
You need something. Yeah, you definitely need a construct of some kind to do this. So I'm gonna give you, one way of doing this. Definitely not the best way, but it will show the logic. Okay. So what this is going to do is to say I have a local variable. So I'm going to use a single bit local variable. If you want to use Boolean, that's fine. We can use a bool here. So bool is going to be the old clock signal, and that's going to be initialized to ram.clock. Okay. So that means I'm sampling the clock pin, and remember the current state of the clock pin as old clock. Okay, that's a one-shot deal. Okay, this is a one-shot deal. And then I get into a loop. And then I get into a loop which says, as long as, okay, every time you see a while, it is really saying the same thing as long as. So, for those of you who prefer to look at your program in a more kind of more of a using normal English words, okay, you can basically do a pound define, which is a macro. Every time you see while, you can say, oh, as long as is saying the same thing. Okay, so as long as old clock is the same as ram.clock, because we are resampling clock in this case. So this is one sampling of the clock pin. This is a resampling of the clock pin and comparing to what it was in the previous sample. Does that make sense? Okay. So as long as it's the same, I'm gonna continue in a loop, and the only thing I want to do in this loop here is absolutely nothing. So when I do get out of this loop, okay, what does it mean when I do get out of this loop? Get out of this loop at this point. Actually, I need to do one more thing. I need to make sure it is 0 to begin with. So let me think about how to do this. Oh, I got it. I got this. Um, because a falling edge, should not, trigger this, to happen. So I need to make sure that, we are stuck in a loop when the clock is not changing, or even when it's a falling edge, it will still be okay. So I need an or statement here. So the or statement is going to say, old clock was a 1, and the current clock is a 0. So if that is the case, I go in here and I say, I have to update old clock, and just basically say it becomes the new clock. Is that okay? Okay, so let's read this code again and find out when we stay in the loop. So how do we stay in the loop? The condition to stay in the loop is an or, which means if 1 is true, we stay in the loop. The left-hand side of the or says, if old clock is the same as clock right now, we stay in the loop. So what that means is the clock has not changed. It was 0 before, and it is still a 0. Okay, that's definitely not a rising edge, right? Or it can say if it was a 1 and it's still a 1, well, we still stay in the loop because that is also not a rising edge. Does that make any sense? And then the next statement says, oh, but wait, even if they are different, we have another chance to stay in the loop. So the other chance to stay in the loop is it was a 1 and now it is a 0. So that means we saw a transition, but it wasn't a falling edge. Excuse me, it's not a rising edge because it was a falling edge. Does that make sense? Because it was a 1, it is now a 0. So it's a falling edge, but the falling edge should not do anything. It's a rising edge that is important to us. So if it's a falling edge, I still want to stay in the loop, but I need to make sure that old clock is now a 1 instead of a 0 as before. So I think a better way to do this is to put a 1 here. Okay? So what does it mean when I get out of this loop? When I end up here, what does that mean?
Does that mean that old clock is 0 and new clock is 1?
Actually, hold on a second here. I need to make one correction. It needs to be a 0 here. Okay, go ahead. Could you repeat that?
Does it mean that the old clock is 0 and new clock is, and the regular new clock is 1?
That is correct. Okay, that's the only way to get out of the loop, right? Old clock was a 0, and then the current clock is a 1. So what does that mean in terms of edges? Okay, first of all, is it an edge? Is it representing an edge or a transition? And if so, is it a falling edge or is it a rising edge?
Rising it from 0 to 1, right?
Exactly. So it is a rising edge because it's transitioning from 0 to 1. But isn't that what I was waiting for? Right? So now we basically say, we just saw a rising edge. The clock just saw a rising edge. Okay, I should say not we, but the clock line just saw a rising edge, which is perfect. Okay, this is the timing control. So now I can say, let's go ahead and update content at the location that the A port is telling us to go to, and it would become whatever ram.d has, which is what the D port has at that point. Okay, so let me just show you the entire code here, because this describes the behavior of a RAM component. Does that make sense to you?
RAM component?
Hmm? RAM.
RAM component.
Yeah, the RAM component. All right.
Basically, you're just, so one, if the clock is on, I guess, then we're just updating that cell, that wherever we're at.
Yep.
And then if it's off, then we're not doing anything.
You mean, okay, let me show the line number and you can tell me which line we are looking at.
So I get the if statement that says if, it's not zero, then it pretty much updates it, but I'm not sure about the else.
Okay, which line are we talking about?
21.
Line 21? All right, so the question is how do we get to line 21? This is the else inside an if, but it's also the entire, there are two ifs, right? So how do we end up here? Let's check the conditions, from the outside. How do we end up here? The first one is, what do we know about ram.cell at this point? Is it a 1 or is it a 0? It has to be a 1, right? The reason why ram has to be a 1 is because this entire conditional statement, did I miss it? No, okay, I did not. This entire conditional statement is inside the if ram.cell does not equal to 1. So that means if I end up on line 23, I already know the ram cell has to be 1. But what else do I know? What is the other thing that I know based on the conditions of the conditional statement, the inner conditional statement? I mean the else branch.
You also know that ram.ld is also 1?
If it is not a 0, which means when it's 1, we do this. So if I do end up at the else branch, what does it say about ram.load? It has to be a 0. That's right. Okay. So these are the conditions for us to end up in the else branch, starting on line 23. So if I continue on line 23, that means I already know the RAM is paying attention because RAM, this chip select is a 1. And I also know that it is in the right cycle because the load pin is a 0. So then it will proceed to wait for a rising edge. In other words, as long as the rising edge of the clock is not noticed, it's not going to do a single thing. It just sits there and go, I'm just going to wait. Now, in reality, it will wait until the select is turned off. Then we go like, okay, I'm not supposed to do anything, and it would just kind of give up the entire thing. But I'm just summarizing, what if the select line stays 1 the entire time, which is a typical way of using RAM. It's very unusual that someone will start with RAM cell being a 1, load being a 0, and then decide, just cancel that. That's very unlikely in reality. Are we doing okay so far? Okay. So this entire description, okay, what I just did here in C code or pseudo C code, you can find it in the library reference as well. So if you go to the library reference of LogicSim, go to RAM or memory library, and go to RAM here, it describes exactly the same thing except with a lot of words instead of pseudocode. Is that okay? There's only one caveat, okay, of reading this document. What they refer to as out is actually LD. So the document and the symbol, they're different because whoever wrote the software at the time changed one, but forgot to change the other one. So what we see here as the out port is really the LD port or the load port. Other than that, okay, this is the documentation. Okay, so reading this documentation can also help you understand how RAM works. Are we doing okay so far? All right. So now that we have a component here, how do we make sure that our understanding of the component is correct? So that's what LogicSim comes in, is we can do some experiments. And that's basically what one of the questions of today's lab is about, is, well, let's do some experiments. So I'm going to do something here. It's going to complain because, I'm going to change all of those at the same time, like that. And then we just select everything, and we go, oh, it won't let me do it. It does not recognize the data bit width of RAM is Oh, because it's different. That's why. Okay, that's fine. Um, I don't want to do your homework, so I'm going to choose something that is not 8-bit wide. So let's just say this is a really oddball, type of processor. Each memory location is only 4-bit wide. And I have to change the input pin and the output pins to reflect exactly that. So both of these will need to change to, okay, shift. There we go. Sometimes it's control click, sometimes it's shift click to select multiple items. There we go. Now it's happy. And then we're going to have all those pins to go to select, and one to go to clock. Hmm? It's not happy on D. Oh. Oh, I just changed the address bit width. And then the output, we'll pick 6-bit here and change this one to also 6-bit. Thank you. And then we just, all the other ones are single bit wide. So here's clock. And then here is load. And then here's clear. Okay, so the first thing I want to do is to demonstrate the destructive nature of clear. Okay, so let's just go to the RAM component. If you change to the poking tool, you can actually just poke and change the individual locations here just by over-typing it. So I can over-type this location, which is location 5. How do I know this is location 5? Tag, you never taught us how to read this whole thing. I cannot figure out why this is location 5. Yes?
Because that's the sixth location left to right, and you can see it's 0 and 4 on each row. So
Yep, that's right. Go ahead.
Oh, my hand isn't raised, but
Oh.
I don't understand what he just said.
Okay, so the question was, how do we know this is location 5? So the question, so there are a few things, okay? So by observation, we see, the gray out, the gray hexadecimal digits on the outside, it's 0, 4, 8, C, okay? So it's different by 4 for each row. And then there are 4 items on each row. So one particular explanation is, oh, so that means, the gray number is the address of the leftmost byte of each row, or the leftmost location of each row. So that means this is location 0, this is location 1, location 2, location 3, this is location 4, which matches the number 4, location 5, so that's why I said this is location 5, 6, 7, 8, 9, 10, and well, this is location A. Remember, in hexadecimal, this is A, location B, location C, location D, location E, location F. Okay, so now I'm going to change this one, since it's already highlighted in red, which means I can just overtype it. So let's just say this one I want to change to, 7. Oh, okay, that won't work. 7A won't work, but 3A does. So I'm going to change the value to 3A. And some of you already noticed this and go like, but 3A doesn't fit in 4 bits. How do you know 3A as a hexadecimal number does not fit in 4 bits? Something about how many bits each hexadecimal number is representing. All right, so let's backtrack. What is hexadecimal? Because we first need to understand when we talk about hexadecimal number or hexadecimal representation, what is hexadecimal?
Base 16.
Base 16, exactly. Okay, so it's base 16. So hexadecimal is just a fancy name of in base 16. So that means each digit in base 16 can represent values from 0 to go ahead.
16?
Close. 15 to 15, exactly. Because in base 10, each digit only represents from 0 to 9, so it's always the base minus 1. But that's good, okay? That's close to exactly what it's supposed to be. Okay, so 0 to 15. And then you think about, okay, let's take the largest value, which is 15. How many binary digits do we need to represent 15? So now you think about the powers of 2, right? So which power of 2 should we start with? The, okay, let's start with 0. So how many ones do we have in, okay, actually, that's not a good way to ask the question. Um, does 15 contain 1? 1, 1. 15. Does 15 contain 1, 1?
Yes.
Yes. Okay, so there's 1, 1, which is 2 to the power of 0. So once we take care of the 1, we only have 14 left, right? So now the next question is, does 14 have a 2?
Yes.
Okay, so once we take care of the 2, now it becomes 12. But then the power of 2 goes up to 2, which is 4. 2 to the power of 2 is 4. So now we ask, does 12 have a 4?
Yes.
Yep. Okay, so now we have 8 left. So the last question is, does 8 have an 8?
Yes.
The answer is yes. So once we take care of the 8, there's nothing left, right? So now we know there's 1, 1, 1, 2, 1, 4, and 1, 8. So how many digits do we need? How many binary digits do we need to represent the quantity of 15?
4.
4 bits. Okay. So that means one hexadecimal digit is taking the place of 4 binary digits or 4 bits. Does that make sense? All right. Okay, let's let that sink in first. One hexadecimal digit is 4 bits. Are we good? All right. So now the next question is, how many bits do I need to represent 3A in hexadecimal?
5.
6. 6 digits, because we know the A, which is 10, 1010, is going to take 4 bits. The 3 is 11 in base 2, so that means we need 1010 for one part of the 2 digits, and then we need 11 for the other part. So it's exactly 6 bits. And the way I configure the RAM is the D port has exactly 6 bits. So each location only can contain 6 bits. Is that okay?
Can you write that out or something like with the, so the 3 is the first part of the.
Okay, let me, I almost got everything up and running, so I just need to share the screen of Zerno. Give me a second to set that up. And then one more to get that to work. Oh, okay. One more, which is start B and C. There we go. Okay. And of course, there's always one last step. And I need to go back to that word. Okay, now it should work. All right. So we were talking about 3. Oh, okay, that didn't work because I was actually poking the wrong thing. There we go. So we were looking at 3A, I think. So the 3 is 0, 0, 1, 1. The A is 1, 0, 1, 0. Is that okay?
Because A is equal to 10?
Because A is 10. Yep. So if when I ask you how many bits are needed, it's not counting the leading zeros on the left-hand side, because you can always pad as many zeros as you want on the left-hand side and not really change the value being represented. So when I ask how many bits are actually needed, that means all the ones here. So there are 6 bits here that are actually needed in order to represent 3A as a hexadecimal number. Is that okay? All right?
What number is that? Is that
In base, you mean in base 10 what it is?
Yeah.
Well, let's figure that out. Okay, so what is 3A in decimal? Hmm?
58.
Okay, so how did you get that?
3 times 16 to the first power plus 10 times 16 to the zero power.
That is correct. Okay, so it goes back to how we interpret the value of a number. Okay, let me throw this out, and you guys can tell me whether you remember this. I think it's m minus 1, m being the number of digits. And then we have digit I times the base raised to the power of I. Okay, do you guys vaguely remember this? Okay, for an m digit number in base b, this is the value being represented in an unsigned way. So the sign representation is very specific to binary, but this works for any base. Are we good so far? I hope so. This is kind of important, right? So when we look at this number, okay, this number here, we say m is 2 because there are 2 hexadecimal digits. B is 16 because hexadeci is 6 plus 10, which is 16. So now what we are really looking at here is for the digit A, which is 0xa, because that means we are looking at hexadecimal digit A. We need to multiply that by 16 to the power of 0 plus 0x3, which is the most significant digit, times 16 to the power of 1. Hexadecimal A is what we know as 10 in base 10. So this is base 10 times 16 to the power of 0, which is just 1, times 3 times 16 to the power of 1. So now we have 10 times 1 plus 3 times 16, and we have 10 plus 48, which is 58 in base 10. Are we okay so far? If you have forgotten how to do base conversion, that's okay. But when you see this, this should remind you of the things that we have done in the past about how to interpret the value represented by a number. Are we okay? All right. So, did that answer the question? Mm-hmm. Okay, very good. All right. All right. So now that we kind of know, the output has 6 bits, and which is also seen here. I mean, if you just look at the diagram, if you look at the circuit, there are 6 bits, to the output. Then how come this is only 4 bits on the other side? Because those two things are independent. One is telling you how many houses are on the street. The other one is telling you how big each house is. So those two things, there's no correlation between those two. Is that okay? Let me say that one more time. The address port, the width of the address port is asking how many bits do we need in order to differentiate all the different locations in the RAM component. So when it's 4, how many locations do we have in this RAM? I'm really asking how many different numbers or how many different values can I represent using 4 bits? 16. 16, very good. So in this particular case, this RAM component has exactly 16 locations. But how big is one location? Well, you have to ask the width of the data port. So in this case, the width of the data port, which you can also see here, is saying 6 bits. So we have 16 locations. Each location is 6-bit wide for this particular RAM component. Are there any questions? No questions? Okay, I can wait a little bit. I can see maybe you're still processing. We good? Okay. So let's say we are good, and this is the neighborhood. Remember, this is a street with 16 houses, and each house can only store 6 bits. So I can go to this location. This is me just poking content into the RAM component. So I can look at this one and I say, I want this location just to store the value of 07. And I go to this location and just say, I want this to store the value of 2, 2E, and so on. So now I have some content that are non-zero in this RAM component. So the first thing we need to know is, uh, what does clear do? If I make the clear pin into a 1, what is that going to do?
Is it gonna, then it's gonna erase all entries, right?
Yep, that's what the description says. Okay, so if you go to the, let me see, right here. So somewhere here it says, I cannot search in this document, but if you look at the pins, so when you look at clear, when this is 1, all values in memory are pinned, all values in memory are pinned to 0, no matter what the other inputs are. I have no idea what they mean by, when pinned to 0, but they're changed to 0, okay? In other words, okay, if you want this to be easier to remember, okay, I know this may not be politically correct, but you can always say nuclear. This is the nuclear option. You basically just reset the entire RAM component, everything back to 0. Okay? All right. So we know what this pin does, okay? And let's just do it, okay? This is just simulation. It doesn't hurt anything. You can see how all 3 locations, got back to 0 because that's what the clear pin is supposed to do. Okay, so not too big of a deal. And let's change one of these locations. I'm going to change this one here to a content of 1C. There we go. All right. So the question now is, first of all, what does 1C look like as a bit pattern? In other words, if I were to display the content of this location over here as the output pin, which is always going to be in binary in base 2, what is it going to look like? What is 1C going to look like as a 6-bit bit pattern?
Well, so we know that we know there's gonna be a 1 to represent the 1. So at least.
But where is that 1? Because we got 6 bits, right? So let me go back to Zernal.
So we know it'll start with a 1.
Okay, so we know there is a 1. Okay, so we're looking at the bit pattern of what again? Okay, let me, I cannot remember what it was. 1C. Okay, so.
And we know that C represents 13. No, 12.
C is 12. That is correct.
And so to represent 12, we need 1, 1, which is 3, plus 4, which is 7.
That's okay. I know C is 1100 because it's 18 plus 14. I know 1 is just 1. The question is, I need 6 bits, right? So the question is, in order to make it this 6-bit pattern, where do I put that extra 0? Do I put the extra 0 here between the leftmost one and the next one? Or do I put a 0 on the other side, which makes the 0 the most significant bit?
Put it in the front.
Put it in front, which means put it on the left.
On the left-hand side.
That is correct. Okay, that is correct. Very good. So this means, I have a 6-bit pattern that should be 0, 1, 1, 1, 0, 0. That should be the output. Okay? All right. So now we switch back to LogiSim, and then we ask that question. Okay? We ask the question of, how do we get the content at this location to appear over here? So there are 2 things you can do to RAM. You're either in a read cycle or write cycle. What would this be? Is a read cycle. Very good. Okay. So if a read cycle, what do I need to do? Which of these ports, okay, is going to tell the RAM and say, hey, you're supposed to be reading a location. Don't change anything. Sure. Let me, oh, that's in the browser. So let me back to the browser. And nope, it's not in the browser. It's in my editor. Sorry, I forgot. There are too many windows. And where's my editor? Oh, I just passed it. Sorry. There we go. Okay. So this is the pseudocode representing the behavior of a RAM component. So how do we tell the RAM component that we want to read something? Yes?
Load.
The load pin, right? So do we want to put a 0 or 1 over there? Because there's a 1-bit port. We want a 1. Very good. Okay. So now we switch back to Logisim. I have to search for all of these things because it's using the same window.
And that also means that the select pin needs to be high, needs to be
Yeah,
open.
but we want to finish the configuration of everything first. So by the time I wake up RAM and say, I got all the instructions for you. So I want RAM to wake up when everything is already set up, so it knows exactly what it needs to do. Because I don't want to wake RAM up and then keep changing the instructions. Okay, because that into the port of RAM in this case. All right. So the 1C is located here. So the question is, what location is that 1C at? It is in decimal 10, but in hexadecimal is A. So those are all correct answers. 10 is right. A in hexadecimal is right. They're all pointing in the right direction. But I need to specify that as a binary number. Yes?
1010.
1010. Very good. All right. So let's go ahead and change this to 1010. Okay, so let's double check everything, right? It's just like, this is pre-flight, okay? Like when an airplane needs to take off, you really hope the pilot and the co-pilot would do a pre-flight check. Like, do we have enough fuel? Is the cargo bay, hatch, closed? Because you really don't want to take off, when you don't have enough fuel or the cargo hatch is still open and stuff like that. So let's check everything first. Do we got the right address? Yeah, I think so. This is 8, this is 9, this is A, and A in hexadecimal is 1010 in base 2. Okay, checked. That's okay. We don't want to take off yet because when cell turns into a 1, we're taking off. Okay, so we don't want to take off until we check everything else. The clock, not important in the case of a reading. Okay, so that's good. LD is a 1 because this specifies this is a read cycle. That's good too. Clear, definitely do not want to exercise that option. So we want to keep that as a 0. Okay, so I think we got everything checked. So now we can say, go ahead, take off. Ding. And you can now see the output becomes 0, 1 for the 1 in the hexadecimal number, and then 1100 for the C in the hexadecimal number. Is that good? Okay. So this is how we perform a single read operation. You have to specify all of those quote-unquote parameters before you proceed and say, hey, go ahead and do it now. All right? So now I want to turn this around. So let's turn it off first, okay, and just say, okay, let's pretend the RAM component is not even here. And this time, I want to change this location over here to, okay, let me just kind of, I'll write that down later. So I want to change this location to a content of, let's say, 36. Okay. So what do we need? What do we need to do? So I'm gonna say, okay. First of all, where is this location? Which location are we talking about? Location 5. Very good. So let me just write down what I'm attempting to do, and then we'll go ahead and do it. So in C notation, what we are trying to do is to do something like this. We want to go to location 5, and change whatever is at location 5 to 3.6, okay, because that's what I said a little bit earlier. So 3.6, and we'll even do another cast here just to be sure. Is that okay? So obviously a char normally has 8 bits, but this time, a char only has 6 bits. Or for those of you who are kind of fanatic about, you know, having the right kind of type, I can do that. So we can say this is uint 6 underscore t, which does not exist, by the way. But but just to be consistent, okay, we'll just say we're dealing with 6-bit locations here. All right. All right. So what do we do? Okay, remember all of those things we need to configure, right? We'll just kind of go in the clock anti-counterclock, no, yes, counterclockwise direction. What do we need to specify at the A port? What kind of binary number do we specify in this case? It's a 5.
So we need to have 0, 1, 0, 1.
That is correct. Very good. So 5 is 1 plus 4. So that means the bit positions corresponding to 1 and 4 should be 1s, and everything else should be 0s. Okay, very good. So let's go ahead and turn this thing to 0, 1, 0, 1. Are you guys surprised that 0, 1, 0, 1 is 5 and 1, 0, 1, 0 is 10? Because, because 1, 0, 1 is 5, and then if you move all the bits to this side, shift it to the left by 1 bit, it becomes 10. Does that make sense to you? Because 10 is, yes, go ahead.
Is that an actual pattern? Are you trying to point out?
Yes.
Like we keep left shifting 1s and then adding a 1 that,
Because left shift is the same thing as multiplication by 2. Why is that? It has to do with, okay, where's my Zerno screen? There we go. So it really has to do with this equation here, this little summation thing here, because by left shifting, we are just moving the indexes by 1. All the ones that are non-zero, they're now 1 more than where they used to be. So the whole number get multiplied by the base. It's just like in base 10, right? Um, what is the ratio of 100 to 100 to 10? 100 is 10 times 10 because of that one extra zero. So in base 2, it's kind of the same deal. 100 is twice of 10 because it has one extra zero, but instead of multiplication by 10, which is the base, it's multiplication by 2. So whatever the base is how you multiply when you're doing a left shift operation. All right, so getting back to here. Okay, this is good. Select, let's not touch that until we know everything else is right. So load, okay, what should it be? It should be 0 because we are attempting to do a right cycle. So LD should be a 0. Very good. All right. Then we got a little problem here. How am I supposed to specify D? Because if you look at the pseudocode, it says right here that once we have the rising edge, I need to look at whatever the D port is, and whatever the D port has, we use it to update the content that is addressed by the A port. But tag, this is an output pin. You cannot specify content with an output pin. What should I do here?
Should you load first the value into D by using what we used before?
No, because there's no way for me to do it. Because right now, D is connected to just an output pin, and an output pin allows me to see what is on the wire, but it doesn't allow me to change it. It does not let me specify what should be, in the wire that it connects to. What does allow me to do that? What is the construct?
Like a memory clock or
No. An input pin, very good. So what I need to do now is to say, this output pin here is great for what we did earlier, but in this case, we need an input pin. So we change this from an output pin to an input pin, and it connects to the same wire, okay? And it doesn't cause a problem, okay? This is all good. And whenever you deal with an input pin, it's good to turn off the 3-state thing. So now, it's either a 0 or 1. let me just go ahead and specify the content. And what is it supposed to be again? 1C? Was it 1C? I cannot remember. Oh, no, it's right here. So we want to specify 3.6, with this pattern here. And what would 3.6 look like as a 6-digit binary number? Whew, okay. So what is the okay, first of all, what is the 6 going to look like? It's going to take up 4 bits, but what is the 6 going to look like? 0110. That is correct. So we have none of 8. Okay, so we have none of 8, 1 of 4, 1 of 2, and none of 1. Okay, that's good. What about the 3? What is it going to look like with these 2 bits?
011.
No. It's just 1 1 because we only have 2 bits to specify the 3, so it has to be just 1 1. Okay, very good. So we got it all set up. And then what do we need to do now?
We need to connect the input pin.
The input pin is already connected. We're all good here in terms of the connection, because if you poke this node, it already has the content that we need in order to overwrite the location of, location A.
The input pin.
Location 5, sorry.
The input pin's writing into the output pin.
Yes. Well, the output pin is just, like an oscilloscope or a multimeter. It doesn't do anything to whatever it's trying to measure. It just tells you what it has at this point. Okay?
It's like almost like a constant in this case. Like we're just forcing it to be that. Just with the input pin.
No, it's not really exactly like a constant. You mean the output pin? The output pin is.
I'm saying what we're doing with the input pin is like.
Yeah,
telling it.
sort of. Yeah, sort of. But the input pin allows you to interactively change the value, and that's why it's not the same as a constant. All right.
The select.
Yep. Okay, so we want select first. And now the RAM component is saying, okay, I'm awake. I know you're trying to specify a write cycle. I know I'm supposed to change the location of 5. I know the new content at that location is supposed to be 3.6. I'm waiting. I'm in the loop. Which loop are we in? We're in the while loop from line 27 to line 30. So now it's in a tight loop sampling the clock pin. It's like, oh, it's 0. Okay. Does 0 equal to 0? Yes. Stay in the same loop. And then we'll do it again. Does 0 equal to 0? Yes. Stay in the same loop. So how do I get out?
You gotta set clock to 0.
Set clock to 1. It's already 0 at this point. Okay, so if you look at this, it's already 0. Okay, this is already 0. We need to change it to a 1. So here's the moment of truth. We can handle the truth, can we? There we go. So that's how you interact with RAM. Okay, the first cycle is a read cycle. This is how you can say, hey, your RAM, I know you have stored a bunch of content. I want the content at that location. Tell me what it is now. And then the other one is to say, oh, wait, I want to change that location. I want to change the content at that location to this over here. Okay? Okay. So we got one little problem. Okay, here, I'll give you some time later on. But I want to fix the problem, because if I want to change back to a read cycle, what do? Well, you just say tack it. That's easy. Okay, turn off select first. You'll set up all the other pins. Let's just say that I want to read back this location, which is location what again? Location A, right? In hexadecimal it's A, which means in the address is 1010. Okay, we know how to do that. I mean, that's what we did earlier. It's a read cycle, which means load needs to be a 1. Okay. The clock doesn't really matter. Let's go ahead and change it back to a 0. It doesn't really matter. If it's a 1, no problem. We don't want to clear, because otherwise, all the content is going to be gone, and that's not my intention. And now we say, yeah, I think we got everything checked out. And then you say, RAM, wake up. Problem. Exactly, because the input pin is still connected to the D pin, so they're screaming at each other. Why is the RAM thing screaming, and what is it screaming? RAM is screaming, I want this pin, okay, this port D, and the wire that connects to it to read 011100. It's screaming at the top of its lung and say that thing, this wire, should be 011100. Okay? Input pin is trying to scream something slightly different, right? The input pin is screaming the same node, which is in red right now because we have a fight. It's screaming, that node is supposed to be 110110. So they agree on certain things, right? They agree the least significant bit is supposed to be 0. Okay, that's a 0 here, and hexadecimal C also ends with a 0. Okay, that's cool, no problem. It even agrees on some of the other pins or some of the other bits, they're ones. But some of the bits, one wants to be a 0, the other one wants to be a 1. And now we have a problem. That's what the E's are representing. The E's are representing the disagreement between what RAM wants to do versus what the input pin wants to do. So what is the easiest way to fix this problem? Well, yeah.
I was going to say, put a transistor in between the input pin and hook that up to your load.
That's right, okay? Because what we want to do, or the easiest way to fix it manually, is to take out this wire. Problem solved, right? So who wants to go into your computer and just, kind of like that all day long? I don't want to do that, right? So what do we want to do? We want to put a clutch here, or we want to put something that can disengage one side sometimes and re-engage it some other times, okay? That thing turns out to be, now this is, I know we're running over the lecture time, but this is going to help with the lab, and that's why I think it's really important for me to finish this. So that thing is under gates, and it's called a controlled buffer. Now, obviously, the control buffer has its own documentation that you can read, okay? It is basically a programmable switch, okay, so to speak, okay? So what we will do is I'm going to put this thing over here. The input, so I'm going to rotate it so it's going to face south in this case. No, that is, well, it complains because I forgot to change the width to 6 bits. There we go. So right now, it has the input connected to the input pin. The output connects to the node that eventually connects to the D port. This is the control port, okay? The control port is basically saying, if the control port is a 0, then the input disconnects from the output. The output is just not doing a single thing. On the other hand, if the control port is a 1, then it makes the connection between the input and the output. Is that okay? So what is going to control the control port in this case? The control port has to go somewhere. So I'm going to route the control port around, and it has to be one of these 4 bits that it has to connect to at some point. But which one do you think has something to do with direction? Yes? Load.
I think it's going to be select.
It is not select, because if you connect it to select, then it is not controlling the direction. The problem that we had to do with the direction of the operation. So the read operation and the write operation, the difference between those two is one wants the D port to be an output, that's a read operation, and then the write operation wants the D port to be an input only. That is the problem. So in both cases, it has to be selected in order to do any work. So having this hooked up to the select port is not going to help, because in both a read and also a write cycle, we need select to be 1, so it's not going to solve the problem. The solution of somehow this has to connect to the load port is correct, because the load port is specifying, is it a read operation or is it a write operation, which implies the direction of the D port is going to change. And that is the essence. That's why we need to turn it off sometimes and turn it on sometimes. I'm referring to the buffer. So the question is, should I just hook it up straight to the LD port? Well, if you connect it straight to the LD port, it doesn't fix the problem.
What do you mean not?
That's right. Okay, so we need a NOT. So we'll hook up a NOT gate and just say when the LD port is a 1, disengage the buffer. And now we got the problem solved. Okay, so this is the very same circuit that you have to do for question number 3. Now the number of bits for the address port and the number of bits for the data port probably would not be the same, okay, because I didn't want to do exactly the same thing that you need to do. But in terms of the circuit, this is what you need to do. But also in terms of how to complete a read cycle and how to complete a write cycle, that stuff is exactly the same thing that we went over earlier in class. So this is why I want to go over this, because it really connects to your homework assignment on your lab for today. So I'm not going to do the same thing where I postpone the due date to like the next class, because I figure out a way to use all the lab computers to do Java. If you brought your own device, you're cool already. But if you want to use the lab computers, I have the instructions to do it. All right. So if you have your own devices, you can go ahead and use your own devices and start right now. For the rest who want to use the lab computers to do that, I can show you guys how to do it, or do you guys can just want to read the instructions and do it based on the instructions? Or do you want me to show you how to do it? I'm good either way. No request for me to demonstrate? All right.
I have a question.
Yeah.
So this was actually RAM. Like, how big would it be? What would the megabytes would it be? Or what would the capacity be?
Okay, so that's a very good question. The question is, if this is actual RAM, how big is it going to be? It all depends on what you're dealing with and how much is needed. So when we go back to the processor, let me see if I can still find the processor here. So the processor that we are working with in this class, if I select this component, I have to be careful so I don't make accidental changes. It has an address bit width of 8, which means it has 256 locations.
Okay.
And each location is also 8-bit wide, which is a byte. So this is a very, very small RAM. It only has 256 bytes. So, but this is only for demonstration purposes for this class, and it's already sufficient for what I need to do with this class. So 256 bytes is okay in this case. So it depends on what you're dealing with. If you're looking at an embedded controller, like what they call an MCU or microcontroller unit, which are the tiny little chips that you put into even wrenches these days. If you want to get a torque wrench and it has a digital display of how much torque it's experiencing, that's typically done by what we call an MCU or a microcontroller unit. So with those, you don't really need a lot of RAM to kind of take the reading of a strain gauge and convert it into base 10 and display it using the display. So with those, you can have even less than 256 bytes of RAM.
Okay.
So it all depends on the application. The reason why you don't want to put in like 4 megabytes or at least something like that is because it takes up die space. So when you manufacture the chip, the RAM is actually takes up quite a bit of space. So you don't want to waste silicon space unless you really need it. To relate it to your question, since you asked that, let me switch back to the browser. And this is thanks to one of your fellow classmates, who introduced me to this, earlier, I think on Monday, right? So this is the Raspberry Pi Pico. Yes, we are talking about you. And this is a chip. This is a controller board they can buy for $4, and that's the entire thing. The processor chip itself is, has a lot less, is less expensive. And I'm just trying to find out, how much RAM it has. All right, so we are looking at the chip itself.
That's cheap. $4.
Oh, that's not for the chip. $4 for the board with the chip soldered on it.
Okay.
So the chip itself is much less than $4. So for this chip, design files, documentation, there we go, data sheet. In my previous life as a software engineer, this is what I read all day long, data sheets after data sheets after data sheets. Um, so let's find out how much RAM it has. And I look for RAM. Okay, there we go. So this thing has 264 kilobytes. That's a lot. Is that correct? Am I misreading that it has 264 kilobytes?
It says SRAM.
Yeah. Yeah, there's a total of 264 kilobytes of SRAM, which is static RAM. So this is plenty. With 256 bytes of RAM for the processor that we're going to use in this class, we can actually write the program of the Tower of Hanoi um, with space left, I think, to explore, to run the algorithm to up to like 5 disks or something like that. Yep.
It's like this little game. Like
Oh, you're showing the animated version?
Yeah. I guess there's like a little. I just googled it real quick as you said it.
Yeah. So
It's
if
like
you.
a game where you have 3 posts and five up to 5 discs, and you try to get them all on one side.
Yep, that's Tower of Hanoi. And if you look at their animations of Tower of Hanoi, and here's one. Okay, now you got one, two, three, four. Oh wait, okay, I forgot. There's this one thing. Okay, now you got three, four, five, six, seven, eight. So we're gonna write an algorithm. I cannot do the animation using the algorithm using the processor, but we can actually go through the same logic to specify from which pole are we moving a disk to which other pole. So we can actually do all that logic with the stack space that is needed, all within 256 bytes of RAM.
Okay.
Yes, so we're gonna write tiny little programs, and trust me, those tiny little programs, they're gonna be challenging.
Can you incorporate C code into the logic zone?
Not directly. That's a very good question because in about 2 weeks of time, I will be attempting to turn every single one of you into a organic C compiler. So you'll be given the C code, and you'll be producing the object code that runs in the processor that we saw earlier. That is one of the purposes of this class. Do you guys remember on the other day I was trying to show you the CID stuff, but I couldn't find exactly what I was looking for? I found it, and it should still be in one of the tabs because I want to show you that because I want to kind of show you what this class is supposed to be about. So this class is supposed to be called Computer Architecture and Organization, which it is not called that, right? It's called what? Assembly Language Programming for Microcomputers. So there's not even a single match of the words, not a single word. Maybe just computer.
Isn't it 4 years?
It's about well, okay. So 3 units of lecture, which means they are not taking into consideration of a lab session like what this part of the class is supposed to be. So if you look at the content of the class, this is the content. We need to talk about bits, bytes, and words. Words are basically just multiple bytes, so I didn't really get too much into it. Um, Numeric data representation and number bases. Remember all the base conversion thing that we did? And today, right? We just did base conversion today. Um, Signed representation, two's complement, those we talked about. Um, we will get into record and array representation. It doesn't make sense to get into that until we talk about the processor. And we are right now in the process, in the middle of talking about the organization of the von Neumann architecture. So we are right in the middle of doing that. Once we are done with understanding each component in the processor, then we can proceed to talk about the control unit, instruction fetch, decode, and execution. So that's in probably the next week. So I want to show you this because this is what this class should be about. And ARC is one of the first, probably the only right now, campus that actually teaching to the CID description. Because otherwise we would have been started on with x86 instruction set on day one. And that's not how we do it. Yep.
I don't know if the lab is available. Is the lab available?
Oh, I haven't released it yet. Sorry. Okay, I got distracted. I distract myself. I'm very good at it. All right, so let me release the lab. Access code is shingles. I have no idea why I use shingles. Shingles. And let me release that. Let me check a few things first. Okay, so we'll show the answer at 1:30 p.m. And do at the same time. Save and publish. There we go. Yep.
I'm going through the steps to try to run it here, but I'm having an issue with one of the commands I need to run. It says it's not able to do it.
Okay, so I can take care of that. Let me stop the recorder. The recorder is actually still going at this point.